All right, for page 27, if you will, please cut out this piece of paper and paste it at the top here. It is your steps for writing quadratic equations in vertex form by completing the square. So what we want to do is go from standard form, ax squared plus bx plus c, to vertex form, which is a parentheses x minus h squared plus k. These are the steps that I'm going to take, and I'm going to use these examples to talk about each of these steps. So I'm actually going to start with example 2 first because it's a little bit easier than example 1. So if you will, go ahead and write down example 2 for me, please. And in step 1, you'll notice that it says to first factor out the coefficient of x squared if not 1. The coefficient of x squared right now is negative 1. It is not 1. You cannot complete the square unless your coefficient of x squared is 1. So what I'm going to do is I'm going to GCF that out. Normally, if this was a solving problem, I would divide everything by negative 1. But because f of x is not an actual number, I cannot divide both sides by negative 1. So the next best thing, mathematically, is to just simply GCF it out. Now, when I do that, this is what I am left with. And I'm going to start the process of completing the square using the x squared minus 6x. And I'm going to ignore the negative 7 temporarily. So step 2 is to take your value of b, which is negative 6. Step 3 is to square that, which now becomes 9. Step 4, in order to complete the square, we are going to add and subtract that same number so that I can end up with a perfect square trinomial. So x squared minus 6x plus 9, that's going to be my perfect square trinomial, so I can actually turn that into a square using tiles. But I cannot add this 9 without going back and counteracting it and subtracting 9 immediately so that I end up with 0. And then I have a minus 7 still inside the parentheses. So now my perfect square trinomial, which is x squared minus 6x plus 9, this would be an actual square. It has dimensions of x minus 3 by x minus 3. So that's x minus 3 squared. I can factor that and get the same thing. The negative 9 minus 7 becomes negative 16. But please keep in mind, you still have that parentheses on the outside that had the negative 1 that we pulled out from the very beginning. And so step 5 is going to be to... we simplified already, so apologize. Step 6 is going to distribute that coefficient back into the problem. So now when I move that negative back into the problem, I end up with a negative in front of this parentheses. It cannot be moved to the inside because PEMDAS says exponents have to come first. And then my multiplication by negative 1. So it's just going to sit here. And then I'm going to have that negative 1 multiplied by negative 16, which becomes plus 16. So example 2 is now complete. I'm now going to move to example 1. So if I start with step 1, moving out the GCF of negative 4 from everything, I get x squared plus 3x plus 2 inside parentheses. If I move to step 2, take half of the b term, which is going to be 3 in this case. Half of that is 3 halves. My tip here is to leave fractions as such. Instead of taking 3 and dividing by 2 to get 1.5, leave it as 1/2 of 3 or 3 over 2. Because when I go to square that in step 3, that is a very easy thing to square. It becomes 9/4. Now, in step 4, I'm going to take that 9/4 and I'm going to add and subtract the same exact number so that I can counteract each of those and make that 0. So I haven't changed the value of the problem, I've just changed the way that it looks. So now that I've added my 9/4 and subtracted it, I now have a perfect square trinomial, x squared plus 3x plus 9/4. If I factor that, the sides of my square, or if I turn this into algebra tiles, the dimensions of my square would be x plus 3 halves by x plus 3 halves, which is the same thing as x plus 3 halves squared. You'll notice at the same time I took this 2 on the parentheses and I actually went ahead and made that into a common denominator with the 9/4. So 2 becomes 8/4. Then I'm going to add my 8/4 and negative 9/4 to get minus 1/4. So that takes care of step 5. I'm going to factor my perfect square trinomial, which I did, and then I simplified the 2 pieces, the negative 9/4 and the 8/4. Step 6 is to distribute that a back in. And so when I distribute negative 4 by this parentheses, I cannot move it inside, so it's just going to sit there on the outside. That'll be my vertical stretch or compression. And then I'll take that negative 1/4 and multiply by the negative 1/4 to become plus 1. So I now can tell the transformations, I can tell the axis of symmetry, and I can tell the vertex, because now you are in vertex form. Next, I would like you to write a note before continuing to step 3 and step 4. The note says you are allowed to factor the a from just the first two terms. It doesn't have to necessarily come from, you don't necessarily have to factor it from each of the pieces, all three terms. So in this case, you'll notice that the 16 is not divisible by 3. So this is actually good because I'm going to take it out of just the 3x squared and the 12x. So when I do that, I don't have to take my c term and divide by 3, because the point is to complete the square of an x squared term that has a coefficient of 1 and a bx term, in this case that's 4x. So I factored out my 3 just from the 3x squared and the 12x. I'm not going to take it out of the 16, although I can, but it makes it 16/3, and that becomes a little bit harder to work with. So now I'm going to do the whole process of completing the square. X squared plus 4x, if you take half of b, which is 2, and square it, that becomes 4. Inside these parentheses, I'm going to add 4 and subtract 4 so I can counteract each of those numbers. And then I have a perfect square trinomial from my x squared plus 4x plus 4. And as a result, the dimensions of that perfect square would become x plus 2 by x plus 2. But there's still this extra minus 4 here on the outside. And there's these parentheses from the GCFing the 3, just from the 12 and the x squared. So now, you'll notice that 16 is still on the outside, but the 3 has to multiply by each piece inside, which is the x plus 2 squared, and then the minus 4. So when I do that, I get 3 parentheses x plus 2 squared minus 12 from the 4 times 3 plus 16. When I add those two, this is my final form for vertex form. Example 3 is now done. I'll do the same with example 4. Step 1 is to take out the GCF. I do not have to take it out from the 1. I can, but I don't have to. So that I don't have a negative 1/2 sitting inside parentheses, I'm going to leave the minus 1 on the outside of that parentheses. So when I do that, I get x squared minus 5x inside parentheses and a 2 sitting on the outside. I can now complete the square using my 1x squared term and my minus 5x. So if I take half of b, which is step 2, that's 5 over 2, and square it, which is step 3, I get 5 over 2 squared. Step 4 is to add and subtract half of b squared and subtract it inside that parentheses. Notice the minus 1 is still sitting on the outside of the parentheses. And 5 over 2, all squared, becomes 25 over 4. That's much easier than doing 2.5 times 2.5. So now really what I'm doing on the inside is adding 25/4 and subtracting 25/4 at the same time. I now have a perfect square trinomial. The x squared minus 5x plus 25/4 can be factored. This becomes x minus 5/2 times x minus 5/2, which is the same thing as x minus 5/2 squared. Now that minus 25/4, it's still inside that parentheses, so I can't do anything with it just yet. So I'm going to go to step 6 now, and I'm going to distribute that back into my parentheses. So when I do that, the 2 will be sitting right in front of the x minus 5 over 2 squared. It cannot move into the inside of the parentheses because of PEMDAS. But when I multiply 2 by 25 over 4, that becomes 50 over 4. And when I reduce 50 over 4, that becomes 25 over 2. So we have minus 25 over 2 minus 1. But 1 also is going to turn into a fraction, which is going to be 2 over 2. And negative 25/2 minus 2/2 just simply becomes negative 27/2. And now this problem is also done. And that's it for this page.